So today on the bench with Eric, we have another donated instrument by a viewer, which is a clock. What does it say? It's a divider and digital clock for fixing the problem that my viewers give me grief about, that our cesium clock didn't give the time. It was a frequency reference. So what do you do to get the time? Well, you use a divider, but more than that, this one also gives you a 1 pulse per second and allows you to change very finely the shift of it. So if you have two oscillators, you can compare them. Hello and welcome back. If you follow the channel, you know that we have had a previous run-in with the HP 5061 cesium clock, a marvel of quantum physics. But as many of you noted, if it is a clock, how come there is no time indication anywhere? And yes, you are quite right, it's written on it. This so-called cesium clock is actually just a frequency standard. See, the fundamental output of an atomic clock is a very stable frequency reference, derived from the vibrations of an atom, not the time. This HP 115BR instrument, though, is a divider and clock, just what we need to derive time from our reference frequency. And it is more than just a visual clock. It outputs a precise electronic tick every second. See the big knob at the right? It is graduated in fractions of a millisecond. By turning it, you can fine adjust the tick reference to within 10 microseconds. This clock is from the early 1960s and was meant to be driven by one of the HP ultra-stable quartz oscillators of the time, such as the HP 106B double ovenized crystal oscillator here at the bottom. You would then synchronize the clock ticks to the beeps of the WWV radio signal from Fort Collins, itself controlled by the large atomic clock operated at NIST, the National Institute of Standards and Technology.
There's WWV.
Moreover, by resyncing it every few days and tracking the dial numbers, you would be able to measure the drifting rate of your local crystal oscillator, a fairly constant rate, enabling you to make periodic preventative tweaks to its frequency adjustment dial. Actually, this fine synchronizing feature would play a significant role in the history of horology in a famous 1964 experiment. HP had just completed a pre-production prototype of the HP 5060A, the first transportable atomic clock. They fitted it in a rack with a battery supply at the bottom, the atomic clock in the middle, and our HP 115BR recognizable at the top. They loaded the whole thing in a turboprop plane and flew it around the world to where other atomic clocks were kept. Moreover, the flying clock HP 115BR was a specially modified model with 10x finer tuning than the standard one. It was therefore able to synchronize the world's clocks to 1 microsecond for the first time in the history of humanity. All this to say that when patron Alan Killian reached out to donate an HP 115, I was pretty excited. Thanks, Alan, for your support and donations. You are a gentleman and a scholar. But of course, like everything else on this channel, it doesn't work. Let's change that. It's super heavy. I think it's transistorized inside, but it still has the tube-based rack. So I tell you, the digital electronics is completely overrated. It's not needed at all. All right, should we open it up?
Let's open it up.
All right. The rack, which is what the R stands for in the BR name, is hermetic and conforms to mil specs. It must have been developed for the Navy most probably. It is sealed with a gasket that's pressed in by a screw mechanism. They need lots of turning.
Oh,
there you go. Ooh. Ooh.
Wow.
Ooh.
It still smells like old electronics.
We have the synchronous motor. Ooh, this is really fine. Milliseconds. Yeah, these are the hundreds of milliseconds. And there is the synchro, I guess, behind this somewhere. And then there's more electronics, we have to move it out. Oh! That's another interesting wire.
Oh, it just stops.
Yeah, we got it further out, it's missing screws and stuff, but you can tell it's really just after the tube era. They are components on, how do you call this, just pegboards?
It's a terminal strip, yeah.
Terminal strips. And there's a lot of RF happening over here. Those must be the dividers. There's added modern goodness in there. The person that donated to the channel said that the divider did not work, so he fed it directly with 1 kHz contraption, which he made with an Arduino, and I suppose that's what this is. Okay, so that's and then we have to find out what modification we're done on that thing. So we found there is a connector on the side for when you powered it from inside the rack. So we're trying to connect ourselves to this. It's powered by 24 volts. Okay, so we're going to try.
Sorry, I just wanted to
check. Double check. With the modification, and then we'll have to back out the modification to try it. Okay, that didn't. Yeah, it's synchronous, so give it a good spin. There we go.
Oh, I spun in the wrong direction.
No, it's good. Oh, yeah, you did spin it in the wrong direction. There we go. Oh, these are...
Oh, that's so
these are
cool.
the milliseconds. That is very cool. And then, if you have a stroboscope, you can actually tell. And this you can just eyeball.
I love that display. It looks like it's a bar graph, but it's really just a painted stripe.
Well, that's pretty cute. So the user provided contraption works, but that's not what we want to do. We want it to be tied to a high precision oscillator. So we have to back out the 1 kHz and get the whole chain working. Well, that's encouraging at least. Out of mercy, I let you feast on the gorgeous insides before diving into the principle of operation, which is quite unusual. It's the early 1960s and we are still in transition from the tube era. Digital integrated circuits are still years into the future, so this baby has to use a heap of clever analog, mechanical and optical tricks to accomplish its noble task. The clock is meant to be driven by a 100 kHz reference signal, at the time a standard output you'd get from a crystal oscillator. Now, how do you divide this using only analog electronics and a few anemic early transistors? You use a mighty RF trick, the regenerative divider. Let's look at the first divider, taking in the 100 kHz and dividing it by 10. It's a weird self-feeding circuit. Let's suppose it's already at steady state and that the 10 kHz signal already comes out of it. It is looped around to a tripler circuit, then another one. So that bumps the frequency up to 30 kHz and then 90 kHz. The 90 kHz is then fed to an RF mixer and mixed with the 100 kHz from the input. As we have seen in previous episodes, a mixer is an age-old circuit that generates the sum and the difference of its two input frequencies, in our case 190 kHz and 10 kHz. The 190 kHz is filtered out and so the 10 kHz come through and the cycle repeats. Obviously this circuit has a mighty chicken and egg problem. You need the 10 kHz in the first place to generate the 90 kHz, which is needed to generate the 10 kHz. So in order to start it, you need an auxiliary startup oscillator that will temporarily inject 90 kHz and jumpstart the whole process. This is done manually with a temporary push button switch inside the unit to get it started. It's a little bit like starting a car engine. This dividing trick is then used again to divide the 10 kHz to 1 kHz. After that, the 1 kHz signal passes through a phase shifter, the one that's connected to our big counting knob. This is implemented by an electromechanical trick using a resolver. We had encountered resolvers before. It consists of a rotor winding for excitation and two stator windings at 90 degrees of each other for picking up the rotation signal. Resolvers are still used to this day in industrial servo systems for shaft angle position sensing. But apparently you can also wire them up as continuously adjustable phase shifters. I won't explain the details, but you can read the explanation in the manual for yourself, link in the doodly-doo. The beauty of this scheme is that resolvers are endlessly adjustable. You can keep turning the thing and retard or advance your signal continuously way past 360 degrees. There is no upper limit. Here, one full turn of the resolver will give you a 360 degree phase shift, which corresponds to 1000 microseconds at 1 kHz. But you can keep cranking it and retard or advance your clock seamlessly by seconds if you wish. Once phase shifted, the 1 kHz signal goes through a power amplifier and is used to drive a synchronous motor. As their name implies, synchronous motors rotate in sync with the frequency that drives them. Ours must have 60 poles or maybe a sub-multiple of that to rotate at 1000 RPM when driven by 1 kHz. You can sure hear the motor sing at the 1 kHz excitation frequency, so this also doubles as a musical instrument, a very annoying one at that. Our synchronous motor is not self-starting. It needs to be spun up close to its synchronous rotation speed before it locks into the driving rotating magnetic field, which is what Eric just did. It will work in either direction as we demonstrated unwittingly. The rest of the division is done by a train of gears until we get to a 10 RPM shaft, which then drives a standard mechanical clock. Then it gets optical. There is a light sensor that looks through a hole on the 10 RPM gear, which gets aligned to another hole on the 1000 RPM disc every second. So every second you get a short pulse from the photocell. However, this would not be precise enough to generate a low jitter tick. Instead, it is used to gate the very stable 1 kHz pulse strain derived from our 1 kHz sine wave. The AND gate lets a single one of the 1 kHz pulses go through every second to give the nicely behaved 1 second reference tick. And voila, atomic precision ticks made with analog electronics, resolver phase shifters and gears. Quite a machine. But our instrument has some modern electronics in it. Alan tells me this is because the dividers did not work. So he just disconnected them and added an internal 1 kHz oscillator. I suppose somewhere here would make sense. Our first step will be to return the instrument to its original configuration, then repair the dividers. So now what we want to do is remove the modification that the user has made and return the instrument back to its original so we can have it be a clock for our 100 kHz quartz oscillator. And I thought it was going to be a piece of cake, but it's not. The instrument in general takes 100 kHz and divides it by 10, phase shifts it with the little knob here, feeds the 1000 Hertz phase shifted thing to the synchronous motor, which turns the clock, which then uses a light source and a little disc to generate a 1 pulse per second. And we already knew that there were problems with the unit because Alan, who was very nice, actually sent us the whole story here, told us that he could never make the divider work and discovered it didn't follow the schematics. So instead, he bypassed the whole dividers and put a 1 kHz sine wave oscillator on it. That's his modification. I thought it was going to be a simple matter of reconnecting those two, but then it turned out way more complicated because Alan was right, it doesn't follow the original schematics. And this unit has been modified 3 times. It has been modified by the user, Alan, but the reason he got confused is that it had 2 HP modifications, and then there's a hint here. This says H27 1115BR, but H27 is if I zoom on it, you'll see that it's in a different font. It has been added later. Then if you look in here, there are some wires that are suspiciously cut. There's some stuff that is not part of the original harness. Nevertheless, they go to boards that are HP branded and with HP components. So something has happened to it. And we eventually figured out the whole thing. So instrument thrice modified. The first modification, that's what Alan did. He cut the green wire and installed his yellow 100 kilohertz here. So, by the way, you are looking at this wonderful noodly diagram from the service manual, which is the block diagram wiring of the unit. Not particularly easy to follow. But the first thing I discovered is that Alan did not put the oscillator before the resolver as I thought, but after it, just before the motor amplifier, and cut a wire just upstream from it. So far so good. But then, when I followed the wire upstream from the cut, I expected it to lead to the resolver, like in this block diagram or the noodle schematic. But it did not. The resolver was apparently wired at a totally different place. The HP modifications had been extensive, and the unit did not follow the original schematics nor the wiring diagrams, which was going to complicate our life quite a bit. Then we went to try to reconnect it and quickly discovered that the phase shifter is not where it should be. HP had modified something. Let me try to reenact my noodly diagram scribbles for clarity. It looks like Alan put his modification downstream of the HP mods, where the unit follows the original schematic again. His 1 kHz oscillator goes into pin S, which is the input of the power amplifier to the motor, a surefire way to get it running again. Then I would have expected that he disconnected the orange wire here, which is the output of the phase shifter, the original signal he should disconnect. Except that I started to look for it, and there was no such connection. Similarly, the input side of the phase shifter, which would have connected to pin V, was also missing in action. Instead, I saw the remnant of a green wire that bridged pin S with pin V. This would have connected the output of the 1 kHz divider directly to the motor amplifier, bypassing the phase shifter altogether. But that green wire had been cut, I suppose by Alan, as this would be the right thing to do to disconnect the internal dividers. So that's excellent news. Alan's modification was surgical and easy to reverse. I just need to remove the modern oscillator and reconnect the HP green jumper. That would get us back to the modified factory configuration with the motor driven directly by the last divider. But what was that mod exactly? Where did HP connect the phase shifter? You might have a suspicion by now. Remember the 1964 flying clock with the modified 1 microsecond resolution unit? What are the chances that we lucked out and got an instrument with the same modification? See this jumper from T to U, which connects the first divider to the second divider in the standard instrument? They removed that and inserted the phase shifter right there. That effectively puts the phase shifter on the 10 kHz line, increasing the resolution by a factor of 10. It's all starting to make sense, but what about the 2 additional boards? What do these do? And then there are 2 cards. So I first reverse engineered the one over here. It turns out it's yet another modification. This instrument has not 1 photocell but 2 photocells. So the 2 photocells, they appear here, but one is not connected to anything. But nowadays it goes through a special card, and this one, I put my scope on it and is 60 pulses per second. And then it simply goes into this board, which I reverse engineered. It's an amplifier. I think it's broken actually. It goes back to here. It eventually shows up over here, and you can tell that they added something. They added one more output, and it's upside down, but it's 60 Hertz. Aha! I think we just figured out modification number 2. Like the first one, it's premeditated. There is already an extra photocell shown in the noodly diagram, shown connected to absolutely nothing. But in my instrument, it is used by the extra board, which, by the way, is also broken. As we will see later, it's not a simple amplifier as I originally thought, but a phase-locked oscillator. It phase locks on the 60 Hz produced by the photocell and generates a reference output. So this unit could also be used as a driver for a 60 Hz synchronous clock, or better, as a 60 Hz reference in a North American electrical power plant. This must be the coolest 115BR on the planet. This unit has a modification which I think makes it 10 times as sensitive or as good in phase shifting. And another modification that adds a 60 Hz output to drive, I guess, another clock that needs 60 Hz. I went on to reverse engineer this second board. This is the pink stuff. It goes with the first modification. If you want to phase shift your instrument at 10 kHz instead of 1 kHz, you also have to sharpen your tick at the output. And this is what this extra board does. Finally, the last added board is the tick sharpener. It takes the fine phase shifted 10 kHz output, combines it with the tick generated by the regular circuitry, and makes it more precise. So that's what the H27 mods are all about. In HP speak, I believe that the H options were customer or military specials and are rarely documented. I could not find any mention of the H27 option anywhere, but I eventually found mention of an H20 option. If you look at the 1969 catalog and the 1969 catalog only, which is the last year this instrument appears, they offer the HP 115BR, but also the H20-115BR. The H20 115BR is modified for plus minus 1 microsecond capability versus the plus minus 10 microsecond of the original, which I bet you is exactly what we saw. And I think the 27 instead of the 20 is because it's a combo of two options. They had this new 60 pulse per second option. So that's it. I think now I understand it and I can start to debug it. I can revert the modification from the user, which I think is just removing this wire and then reconnecting it here. Now I understand the pass between the first divider and second divider going through this. I should be able to debug it, and that thing is its own independent thing. So from my early trial it doesn't work, but that shouldn't be too hard to repair either. Yeah, it shouldn't be too hard to repair, says a confident CuriousMarc. But that is seriously underestimating the fight that the regenerative divider is going to put up before we can finally admire our continuously adjustable phase shift and make a proper atomic steampunk clock. To be continued in the next restoration episode. See you then!